Now let's look at a different notation for differentiation. This is called the Leibniz Notation. Now the idea here is that if we had the chord here, and if the point B was to get closer and closer to point A, we've seen that the gradient of the chord would tend towards the gradient of point A. So that's what we did whenever we were doing our differentiation. So what we do is we look at this distance here, which is the rise of the chord, so it's just the height of the chord. Now if we call that delta y, and then we call this distance here, which is the run of the chord, we'll call that delta x. Now whenever we take delta y upon delta x and we take the limit as delta x tends towards 0 of that ratio, then we can rewrite the f derivative of x as dy by dx. So let's go ahead and we'll write that out and it'll become more plain and obvious as to what it means. I've drawn a function out here in red, so this is our function f of x, which we are going to find the derivative of. Now we've seen whenever we found the derivative that if we were to draw a chord between 2 points in this function, then we let this point tend down towards this point here, then the gradient of this chord will tend to the gradient of the point here. So the new notation that we're going to use is the Leibniz notation, and we think about the gradient of this chord has been given by the rise delta y divided by the run delta x. So that little triangle is just the delta, means a small change in y and a small change in x. So if we take the gradient here, delta y upon delta x, but we take it as the value of delta x tends towards 0, it gets smaller and smaller, then we're taking in effect the gradient of the chord as it tends down towards just this single point. So we say the limit as delta x tends to 0 of delta y upon delta x. That is given that the new Leibniz notation is dy by dx. So this dy by dx is the derivative of the function f of x. It's the same as writing f dash of x. So I've written it again out on the right hand side. So the limit as delta x tends to 0 of delta y upon delta x equals dy by dx. And that's the same as the f derivative of x. It's just a different way of writing it. Now this method here is a preferred method of writing out the derivative, because it reminds us that what we're doing is we're taking the limit of a ratio here. So we've got a ratio here, but it's the limit of a ratio which gives us the dy by dx. So here's an example of how we use it. If we wanted to find the derivative of x squared, we could write d by dx of x squared equals 2x. So that's all there is for this video. I'll get you in the next video. Goodbye.